So far in this module, we've been looking at logical propositions and focusing on how we can combine simple atomic propositions using connectives to form more complex propositions. In this video, we're going to return to the question of how to know when a complex or molecular proposition is true or false, and we'll use the results to answer another question from the last video about how to know if two superficially different propositions are logically the same. Just to remind you, in logic, we deal with statements that have definite and knowable truth values. Complex statements, which we've called molecular, are built up out of simple or atomic statements joined by logical connectives like and, or if-then. Remember that one of the basic rules of logic is that the truth value of a complex statement is determined only by the truth values of the simple statements that make it up and the types of connectives used, and nothing else. The precise rules for how to find the truth values of these complex statements are spelled out in what we call the truth tables for the connectives. A truth table for a statement is a table that lists all the combinations of the truth values of the atomic statements involved, and then for each of those combinations there is listed the truth value of the molecular statement. Here's a basic example that we saw earlier for the conjunction or and connective. This connective joins two statements, P and Q. Each of those two statements has two truth values, true or false. And this gives rise to four possible combinations of truth values, which we list in separate rows. The conjunction produces a true statement when both the inputs are true and false otherwise. This is just a summary of how the word and normally works in our usual language. So this truth table tells you the conditions under which the conjunction is true as determined by the truth values of the two statements involved. What's powerful about truth tables is that the content of the atomic statements doesn't really matter. Any two statements joined by and will have the same truth table. This allows us to perform one of the basic conceptual leaps of computer science, abstraction. This means that we can ignore the details of this construction and focus only on its general structure. We also saw truth tables for disjunction, or, as well as a truth table for conditional statements, or if-then. In each of those situations, the connective still operates on two input statements, and the final statement's truth value is determined by the truth values of the inputs. We also saw a truth table for negation, or not. This one was different than the others because it only works on one statement, but the truth value of the result is still dependent on the truth value of the input. Computers handle many logical operations like these four using what's called a logic gate. This is often a piece of hardware that's the building block for an entire circuit that processes logical values using bits, 0 for false and 1 for true, in the form of electrical signals. For us, logic gates are a handy way to visualize what's happening in a truth table. Here's a diagram that represents a logic gate for AND. The connective is the shape that looks like a circuit, and it has two inputs, A and B. Each of these is a Boolean value, either true or false, or 0 or 1, and the output is called Z. The truth table here is a binary version of the truth table you saw earlier. Down below it is the logic gate diagram for OR, and here's the one for NOT. In fact, you can search and find a host of logic gate diagrams for all sorts of connectives, many of which we haven't seen here. You might notice there isn't one for if-then. Now, why is that? Well, you'll have to stay tuned to the next video for that. One very important use of truth tables is to give us a rigorous answer to the question of whether two propositions are logically the same, even though they may look different. This came up in the last video when we noticed that a conditional statement and its converse can sometimes have opposite truth values, while the statement and its contrapositive appear to be the same. We say that two propositions are logically equivalent if they have the same final truth value in each possible combination of truth values of the simple atomic statements that make them up. This means essentially that the two statements are logically the same, even though they may be phrased differently. We can use truth tables to know when two statements are logically equivalent and when they aren't. Let's look at if P then Q. Here is its truth table, which we saw in an earlier video. Now let's set up a truth table for its converse, if Q then P. To set up the truth table, we list the atomic statements in columns like this. I'll keep the ordering the same here with a column for P to the left of the one for Q. Now we create a row for each combination of the truth values of the atomic statements. Since there are 2 of those, there are 4 truth combinations, and I'll keep them in the same order as in the first truth table. Then I'll make one column over here for the final proposition. Now in each row, let's use the connective to determine the truth value of the final result. The statement we're working with here is if Q, then P. Very importantly here, remember that a conditional statement is true in all cases except when the hypothesis is true, but the conclusion is false. It doesn't matter what the hypothesis or conclusion are. In this case, the hypothesis is Q and the conclusion is P. So we're going to go one row at a time and determine the truth value. In the first row, P and Q are both true, so the hypothesis, Q, is true, and the conclusion, P, is also true. That makes the entire conditional statement true. In the second row, P is true and Q is false. This means the hypothesis of the conditional statement is false, and the conclusion, which is P this time, is true. Remember that in such a case, the entire conditional statement is true. Let's stop for a moment. The hard part of this process is that we have to think about how the proposition is put together in each row and not just copy from an existing truth table. You might have wanted to put false in the second row because in the truth table for if P then Q, it was false in the second row. But this isn't if P then Q, it's if Q then P. So here we have to remember that Q is not the conclusion, it's the hypothesis. Now you take a moment to fill in the last 2 rows of the truth table. Pause the video and then come back for a debriefing. So in the third row, we have P false and Q true. In the conditional statement, if Q then P, this means the hypothesis is true and the conclusion is false. That's the one situation where the conditional statement, if Q then P, is false. And so that's what we put here. Then finally, in the last row, we have both statements false. In particular, the hypothesis is false, which remember makes the entire conditional statement true. Now I'll pull back and look at both truth tables. We see here that the original conditional statement and its converse are not the same truth value in all the same situations. In particular here, when P is true and Q is false, if P then Q is false, but if Q then P is true. So that means the conditional statement and its converse are not logically equivalent. What about the contrapositive? We caught a glimpse in the last video that maybe the conditional statement and its contrapositive might be logically equivalent. But are they? What does the truth table for the contrapositive look like? Stick around to the next video to find out.